So I wanted to put together a video that had several examples for solving exponential equations using logarithms. Um, there are many examples that you could do, that you could be presented with, but the reality is they all sort of follow the same format. Some of them you'll be able to give decimal answers. Some of them you're asked to give exact answers, and we'll address those in the later examples. But I just wanted to run through a few. It's actually more than a few from the textbook that was sort of similar to homework questions that you'll be looking at that will apply logarithms in order to solve for the exponent in an exponential function, which is, last section we looked at, or last chapter we looked at doing those with graphing. And so now we're using logarithms, whether it's a common log of base 10 or a natural logarithm of base e, to try to solve some problems. So we'll do this to begin with. So here come examples. So let's solve for x. 2 to the x equals 11. What power of 2 would give you exactly 11? So the format that you want to try to aim for solving before you apply any logs is you want to have a single number with an exponent equaling everything else. So you want to get that base with the exponent alone, and then what we're going to do is we're going to do what's called taking or apply the log of both sides, because the logarithm is just a function, sort of like if you square root both sides, or if you raise both sides to a power, if you divide both sides by 2. The logarithm is just a function that we're going to apply to both sides of the equation and then use our properties of logarithms to solve. So for this one, if my 2 to the x is alone, my 11 is away from the exponent. So what we're going to do is just apply logarithms to both sides. And you can use natural logarithm or you can use a common logarithm, but the natural logarithm is used a lot when the base is e. If it's not, you're welcome to use either one, but I'll be using just the common logarithm. So if I take the log of 2 to the x and take the log of 11, I just applied a logarithm to both quantities of the equation. Then you get to use log rules. So if you recall before, if you have, it's the power rule that says if you have the log of something to a power, you can bring that power down front and multiply it by the log. So that's what we're going to do here. We're going to take this x, and it's going to hop out front as a product, and we have x times the log of 2 equals the log of 11. The log of 2 is just a number. The log of 11 is just a number. I'm trying to solve for x, so I'm just going to divide by the number log 2, divides it away from the left side, and I have that x equals the log of 11 over the log of 2. And no, you can't make that log of 9 or make it 11 over 2 and split it. The logarithm laws don't work that direction. So you can just, in your calculator, type in the log of 11, close the parentheses, and divide the logarithm of 2, and you'll get that x is approximately 3.4594, depending on how many decimals it asks you to round to. So that's the power on 2. If you look back at our original problem, 2 to the 3.459 power will come close to 11. Again, it's rounded, but 2 to that exact power would give you 11, and that's the solution for this problem. Okay. Another example. Solve. So solve for the variable here. We have e to the 0.12x equals 100. So if you remember from the last chapter, this is sort of in the format of a continuous growth function where it's growing at 12%, and you're trying to find out when it equals 100. And again, before when we did these, we sort of just graphed them, found out where they intersected. And that's a graphical way to find the answer. But using and applying logarithms is an algebraic way to find those. So because our base is e, I'm going to apply the natural log to both pieces. Because if I do the natural log of e, it'll cancel each other to 1. So if I do natural log of e to the 0.12x equals natural log of 100, again, you have to apply that natural log to both sides of the equation. The natural log of e is just 1, and you're left with the 0.12x. Or if you wanted to think about it, the 0.12x comes down as a product. Natural log of e equals 1. You're still left with 0.12x equals the natural log of 100. Solving for x, we'll just divide by the 0.12. And x is the natural log of 100 divided by 0.12. And again, it has a decimal in the denominator, so I'm not going to say it's exactly exact. But if you wanted to type in ln of 100, please be sure to close the parentheses before you divide by 1200ths, or it'll keep that in the parentheses and that'll be wrong. So for this one, natural log of 100 divided by 0.12 will give you 38.3764 if I round to 4 places. Okay, so that's the value of x in our e to the 0.12x equals 100. Again, it's what you would get for the x value if you graphed it, found the intersection, but this is using logarithms. Okay, here is another example. Say you had 10 equals 22 times 0.87 to the q power. If you go back to the formatting thing that I mentioned before, you really do need to make sure that the base that has the exponent is alone before you take the logarithm of both sides. So in this example, I'm going to go ahead and divide away the 22 so that the 0.87 to the q power is alone, and then I can apply the logarithm best. So if I just divide both sides by 22, when you do 10 over 22, if it's a decimal, you're better off leaving it as a fraction, a simplified fraction. So 10 over 22 reduces to 5 over 11, which is like, I think it's 4545545 repeating. Yeah, so don't round that to 0.45. Make sure you keep it exact. Keep it 10 over 22, reduce it to 5 over 11. But either way, you need to keep that exact. And now we're left with that equals 0.87 to the q power. This is a decay function like we had last chapter. The base is not e, so I'm just going to use and apply the common logarithm to both sides. So what that'll look like is the log of the quantity 5 over 11 equals the log of 0.87 to the q. We'll use our exponent property to said if I take the log of a number with a power, that power can hop down front as a product. So I have the log of 5 over 11 equals q times the log of 0.87. I'm solving for q, and currently it's just being multiplied by a number. So I'm going to divide both sides by the number log of 0.87, canceling it from the right, and I get that q is this nice quotient of logs, log of 5 over 11 over the log of 0.87, and calculator-wise, again, you do the log of the 5 divided by 11 quotient. There's no reason, you could split it. It would be the log of 5 minus the log of 11, but neither one of those are helpful, so we'll just leave it log of 5 over 11. And then divide that by the log of 0.87. And when you do that, you get a q value that's approximately 5.6617. So that's the answer for that example. Okay. Another one. So say you had 48 equals 17 times 2.3 to the w power. Okay. Again, just like in the previous example, the portion that has the base with the exponent that we're trying to solve for, you want to get that alone. So I'm going to divide away over the 17 so that I'm left with 2.3 to the w on the right and a not reducible fraction of 48 over 17 on the left. Please leave it as is and don't round the decimal. And now I can apply logarithms or logs to both sides. I'm just using the common log. Again, I don't feel the need to use a natural log unless it's e, but you could use that if you wanted to. You do get the same answer. So the log of 48 over 17 equals the log of 2.3 to the w. Again, log of a number to a power, I can bring the power down. So I have the log of 48 over 17 equals w times the log of 2.3. Solving for w, so I'm going to divide away the logarithm of 2.3 because, again, it's just a number. And that makes w this really nice log of 48 over 17. Again, keep the 48 over 17 together because that's what you're taking the logarithm of, and then divide that by the log of 2.3. And this is for calculator entry. And you should get that w is approximately 1.246. Again, watch the number of places you have to round it to. But don't round any other decimal until the very end of the problem, or you'll have a lot of carryover error and you won't be able to catch your mistake. Okay? Let's do some more here. Say you had the problem 2 over 7 equals 0.6 to the 2t, so something other than a single variable in the exponent. You still have a base to a power, so at this point you can apply logs to both sides. So again, I'm just going to use common logarithm. The log of 2/7 equals the log of the 0.6 to the 2t. The 2t is the entire exponent, so that will allow me, using logarithm properties, to bring that 2t down and make it a product times the log of 0.6, and that equals the log of 2/7. Again, please don't round the 2/7 to a decimal, just leave it 2/7 as a fraction. And now I need to solve for t. So there are two things that I have to get rid of, and I can get rid of them at the same time. I need to divide away the 2 and the log of 0.6. If you want to do those in 2 steps, you can, but you can do them all in the same step. Divided by 2, log of 0.6, gets rid of the 2, gets rid of the log. Just be really careful on calculator entry for this, because you'll have to do log of 2 over 7 and close it. You can get an answer there if you want, but you'll divide that by the quantity of 2 times the log of 0.6. Again, if you divide the log of 0.6 and then divide the 2 separately, again, the calculator operation is up to you. But in doing so, you get that t is approximately 1.2262. Okay. Another example. These are going to get into where if the directions say to solve exactly, they're at the end of section 1 for this textbook, then you're going to leave either the log or the ln in the actual answer. And I'll show you several of those so you can see what I mean. Because there is a decimal approximation for all of them, but if the directions say, and you'll have to pay attention, if they say to solve exactly and they don't tell you decimals to round to, don't just make it up. You need to actually give exact answers for this problem. So we'll start with 3 times 1.081 to the t equals 14. Again, we've seen some of these, this was an 8.1% exponential growth function from our last chapter, but we're not graphing it right now. We're going to apply logarithms, but the first thing I need to do is get that base with the power by itself. So I'm going to divide both sides by 3 and have 1.081 to the t power equals a fraction of 14/3. Do not give the repeated decimal for that. I know it's tempting because it's easier, quicker to write, whatever, but don't write the 4.6 repeated. Leave it 14 over 3. I'll apply the logarithm to both sides, just a common logarithm. So the log of 1.081 to the t equals the log of the fraction 14 over 3. I can bring my t power down, multiply by the log of 1.081, and that equals the log of 14 over 3. Solve for t, so I'll divide both sides by the logarithm of 1.081. And that leaves me with t equal. So there is a log of a quotient, and there is a log property that says you could take those and subtract them. But because the log of 14 and the log of 3 are neither nice log answers, it's sort of a useless thing to think about for this. I mean, you can think about it, but you can't use it for anything. And you have two different logarithms, and you can't, combine those at all. So really, even though it doesn't look so pretty and exact, the exact answer for this is the log of 14 over 3 divided by the log of 1.081. Like, don't even type in the logarithm function. Don't even do the number. Leave it exactly. I mean, if you'd like to know the decimal approximation, it was about 19.7781. But if you enter that in for your online homework in Wiley, it will not work. It'll tell you that it's wrong, and you'll wonder why. And so this one that I've put the box around is exact. So leave it as the log of 14 thirds divided by the log of 1.081, and you'll be good. Okay, let's do another one. Okay, how about solve exactly? Again, the rest of these will be solve exactly. 84 times 0.74 to the t power equals 38. So it's another exponential decay function. We need to get the 84 away, like divided away, because it's being multiplied. So that's where we'll start with this one. We'll divide both sides by 84, and you're left with 0.74 to the t power. It equals 38 over 84. Now that fraction simplifies. There was an example in the textbook that left it 38 over 84, but it does simplify to 19 over 42. So I'd like to think that you should be able to simplify a fraction if you can, but do not use the decimal. No e's here, so I'm just going to apply logarithms to both sides. So I'll take the log of 0.74 to the t power equals the log of the fraction 19 over 42, or 38 over 84. It'll be the same answer. Bring the exponent down front as a product. So you have t times the log of 0.74 equals the log of 19 over 42. Divide both sides by the log of 0.74. And you'll get that t is, so again, we're in the same boat we were before. None of those are nice powers of 10 to be able to get a non-logarithmic answer. So the exact answer is what you're looking at, the log of the fraction 19 over 42 all over the log of 0.74. And that's how you would answer for the homework, is the exact fraction of those two logarithms. Okay. Here's another example. 40 e to the negative 0.2t equals 12. So this has an e as a base. So I'm actually going to use the natural logarithm here whenever I apply. But the first thing I want to do is get rid of that 40 so that I have it not on my base of e, and I can apply the natural logarithm easier. 12 divided by 40 does simplify to 3/10. So you can use 0.3 or you can use 3 over 10, but it's not a decimal that we rounded. It's an ending truncated, terminating decimal, so we can just use 0.3, that's fine. And now I have my e to my power, so I'm going to apply the natural log to both sides. So I'll do the natural log of e to the negative 0.2t equals the natural log of 0.3. You would not want to use a common logarithm here because of the base of e. You would want to use the natural logarithm. And the natural log of e, if you remember, that's going to be 1. Or if you want to think about it, the exponent comes down times the natural log of e, which again is still just 1. So we're left with negative 0.2t on the left equals the natural log of 3/10 on the right. I'm solving for t. It currently has a negative 2/10 multiplied by it. So I'll divide both sides by negative 2/10. And I'll get that t is the natural log of 3/10 divided by negative 2/10. And again, there's nothing, you can calculate and get the decimal for it. It's approximately 6.0199, but there's nothing to really do to make it look prettier in the sense of exact. So the natural log of 0.3 divided by negative 0.2 would be the exact answer for this problem. Okay, do a few more. Another one with E. This is another one where you solve exactly. So we'll solve exactly for e to the x plus 5 equals 7 times 2 to the x. Now this one's a little bit different, so I wanted to make sure to work through it in this video of examples. There are two places that have an x in them, so there's not really anything to move here to begin with, but you do have your e with an exponent alone. So, and because we're having a base of e, it makes sense to use and apply natural log versus a common log. So I'm going to use and apply natural log to both sides. So what that'll look like is natural log of e to the x plus 5 equals natural log of the quantity 7 times 2 to the x. So the left side, natural log of e to a power, you're just left with the x plus 5. Again, however you want to think about that, the natural log of e ends up being 1, and that exponent hops down front as a product, and so what you're left with is just the quantity x plus 5. What happens on the right-hand side, though, is a product, is a natural log of a product, and if you remember from your log properties, if you have a log of a product, you can rewrite that as a sum of those two things. So I can rewrite natural log of 7 times 2 to the x as the natural log of 7 plus the natural log of 2 to the x. Again, that's just using an x or a logarithm property from some refresher ideas that we've talked about before. The natural log of 7 is just a number. I still am trying to get the x's together, so I can use my log properties on this right term, this natural log of 2 to the x, and bring that guy down front. So I have x plus 5 equals natural log of 7 plus x times the natural log of 2. The two terms that have x's on them, I need to get those on the same side of the equation, and the other terms not. So I'm going to subtract the x natural log of 2, and then the 5 that was over here on the left, I'm also going to subtract it to the right side of the equation. And note here that whenever you do the natural log of 7 minus 5, it is not, and I repeat, not the natural log of 2. The natural log is tied to the 7, the 5 is an afterthought. You cannot combine those. It's like, combining like terms. Those are not like terms. The natural log of 7 is a decimal, 5 is an integer. Leave it just like that. The left-hand side, they both have the terms with x's on them. So just like we've done before in solving for a variable where it appears twice, I'm going to factor the x out, and what that will leave inside is a 1 minus the natural log of 2. That equals the natural log of 7 minus 5. And then I'm going to divide by the quantity 1 minus natural log of 2. The whole quantity, not each piece. So x is exactly natural log of 7 minus 5 over 1 minus natural log of 2. And it's approximately negative 9.95, but you have to be able, for this particular problem, to give that exact answer using those natural logarithms in that quotient form with the correct subtraction. So just be extremely careful of that. And again, the 5 here is not in a natural log quantity, so you need to hop out of it and subtract 5 in the numerator separately from that natural log. Okay. Here's another one with a slightly more complicated exponent, and it's a solve exactly, but it's 100 to the 2x plus 3 power equals the cube root of 10,000. Okay, so there's a cube root, and just like with any roots that we've had before, and we're dealing with exponents, it's going to benefit you to think about that in exponent form. So if you remember, square root was a power of a half. If it's a cube root, it's a power of a third. So we can rewrite the cube root of 10,000 as 10,000 to the 1/3 power. And now that I have, where the variable I'm trying to solve for is in an exponent, I can apply logarithms to both sides. So and it's alone, that term, so I'll apply logs. So do the log of 100 to the 2x plus 3 power equals log of 10,000 to the 1/3 power. We'll use our exponent property that allows us to take exponents down front as a product on both sides here, actually. And we'll have the quantity 2x plus 3 times the log of 100 equals 1/3 times the log of 10,000. Those logs are nice logs, but I like to call nice logs because they're nice powers of 10. So if you evaluated the log of 100, it's like the power of 10, because it's common log, power of 10 that would give 100. So that value is just 2 times our 2x plus 3. And if you do the log of 10,000, that calculation is, if you remember, the power of 10 that gives you 10,000. In that case, it's going to be 4. So if we evaluate those logarithms exactly, and we can because they're powers of 10, we come up with some prettier things. I still need to solve for x. So you can either divide 2 at this point, or you can distribute it through. I'm just going to distribute it through for visual. 4x plus 3, not 3, 4x plus 6, apologies. 2 times 2x, 2 times 3 equals 4x plus 6. 1/3 of 4 is 4/3. Subtract 6, you get 4x equals, again, keep it exact because it's in thirds. It'll have a decimal, it'll repeat. 4/3 subtract 6 ends up being negative 14/3. And then if you divide by 4th or multiply by 1/4, again, process is up to you, but divide by 4 or multiply by 1/4, you get the same answer. It ends up being negative 7/6, which again does repeat, so the exact answer needs to be given as negative 7/6 for this problem. So this uses the exponent property for logarithms, and it uses some common logarithm powers of 10 that makes the answers a little easier to come up with. It's not so easy when they're not powers of 10, but when they're powers of 10, they're not too bad. Okay. Just a couple more. So if we had an E1, 58e to the 4t plus 1 equals 30, and you had to solve for the exact answer. Okay. So again, it's an E base. I'll use natural logs in this one, but I need to divide that 58 away to make this more nice to solve for. So e to the 4t plus 1 equals 30 over 58. That does reduce to 15 over 29. You can keep it 30 over 58 as long as it's exact, but it does round. I mean, it does not round, it simplifies. We'll apply natural logs here. So we'll do the natural log of e to the 4t plus 1 is the natural log of the fraction 15 over 29. Same thing again, when you do natural log of e, that portion's 1. You're left with just the 4t plus 1 equals the natural log of 15 over 29. You're solving for t. Currently, t has a 4 multiplied by it and then a 1 added to it, so we need to subtract away the 1. And we get 4t equals natural log 15 over 29, subtract 1. And then the 4 being multiplied by the t, we need to get rid of it, so you can either divide by 4 or multiply by 1/4. I don't really have a preference. But t ends up being natural log of 15 over 29 minus 1 all over 4. Or if you went the 1/4 route, it would hop out front times the natural log of 15 over 29 minus 1 as a quantity. Those are both the same answer and should be accepted as such. But that would be your final exact answer for this problem. The decimal approximation, again, you don't really have to come up with it because this one's going to ask for exact. But you can always get the number for that and compare it to what you would have gotten graphically, because this was you could graph it like we did before. Last one. So this last example it sort of uses some additional log properties, which is the only reason I kind of wanted to display it here. So if you had, again, this is another solve exact, 6,000. So if you had this problem, 6,000 equals 1/2 to the t over 15 power equals 1,000. This one, it has a 1/2 as a base. The exponent has a fraction, so this is just slightly different, but the same rules still apply. We need to get the base with the exponent alone. So I'll divide away the 6,000 to both sides, and you're left with 1/2 to the t over 15 power equals 1/6. Again, please leave exact because that is a repeating decimal, and you don't need that. I'm going to use a logarithm here. You could use a natural logarithm if you wanted to, but there's no e, so again, I'm not compelled to use natural logarithm. So I'm just going to apply logs to both sides, and that'll give me a log of 1/2 t over 15th power equals a log of 1/6. I can bring my power down. T over 15 times the log of 1/2 equals the log of 1/6. All right, so I need to get the t alone. So to begin with, I'm just going to multiply both sides by 15, just because that would get rid of the 15, and now I wouldn't have to worry about it. So I have t times the log of 1/2 equals 15 times the log of 1/6. So here's where this problem gets a little more interesting. I realize that 1/2 is 0.5, and I realize that 1/6 is some decimal that doesn't, what is it, like 167 or something like that? Yeah, 1666666 repeated. So the repeating one is not helpful, but within those fractions of those logs are values that have nice answers. In other words, whenever we did logarithm properties to begin with, if you had the log of a quotient, you could rewrite that as the log of the top minus the log of the bottom. And the only reason I say to separate that here is because we know that the log of 1 is going to give us 0. So if I take those separately and rewrite log of 1/2 as log of 1 minus log of 2, and the same thing for the 1/6, I can rewrite that log of 1 over 6 as the log of 1 minus the log of 6. And what happens here, again, just to make it more exact, the log of 1 is 0. Remember, it's like what power of 10 would give you 1? So the log of 1 is 0, and we have 0 minus log 2 equals 15 times 0 minus log 6. The 0 minus those quantities simply become negative logs. So we have t times negative log of 2 equals 15 times negative log of 6. You can divide away the negative log of 2. T is now by itself. Yes, the negatives, they're not in the logarithms, they're on the logarithms, sort of like coefficients of -1. So those do cancel to positive, and you have 15 times the log of 6 in the numerator and the log of 2 in the denominator. And no, you cannot make 6 divided by 2 3 and say that's the log of 3. Log properties do not work backwards like that, or they don't work in the direction where there's two separate logs being divided. So the exact answer here is 15 log of 6 divided by the log of 2. So I felt like going through this example to show you that you still may in the background have to apply some of those log rules that will help clean up some of your answer, because otherwise you would have had like log of a half and log of a sixth. And the fact that you can take the log of the number 1 nicely, you need to go and do that. Whereas in the previous examples, it was, log of 15 or 29 or 3, or, if it's a log that you can take a nice number of, whether it's a natural log or a common log, you need to be able to pick those out and do that to solve for those functions.